So now we're going to talk about something dear to me, corrective lenses. So this has to do with how your eye, you got a lens here on the front of your eye, you got the retina back here. So what happens is you see an object out over here, and you end up with a real image here. So it's inverted, okay, and it's going to be smaller, obviously, than the tree or building, whatever you're looking at. But what happens is your eye, the lens, in order to focus, what happens is you have muscles that squeeze the lens. When you squeeze the lens, changes the curvature and changes the focus. So you squeeze the lens, the focal length gets shorter. That allows you to focus a shorter distance back onto the retina. And so when you relax the eye, that's when you see the farthest away. You can only squeeze the lens so much, and that defines the closest point you can see. The closest point that you can see is called the near point. The farthest thing you can see is the far point. Now, the far point is supposed to be infinity. Okay. The textbook definition of near point is 25 centimeters. So that's the textbook. So this is, this is not exact. Now, a camera lens works the same way. So you have a camera, okay, and you got a lens on the camera, and you've got the image plane back here. In modern camera would be a charge coupled device or a CCD chip. And so if something out here changes distance, then you need to change the lens. Well, you can't change the focal length of the lens, so the lens moves in and out some. So think of it like an SLR camera. When you focus, you're changing the lens in or out. With your eye, you're actually squeezing the lens and changing the focal point. Now, one of the problems that sometimes happens is with the lens, the focal length ends up wrong. Okay, so for example, genetically, you could have an eye that's a little bit too long, or a lens that is too thick, and so the focal point is too short and doesn't go back to the retina. So what that means is the far point is not equal to infinity. And so in that case, you need to put a corrective lens on here to fix the eye. So let's do an example. So we have an eye right here, and let's say that the far point, and I'll just abbreviate far point as FP, and so let's say that's 1.7 meters. Near point, might be 21 centimeters, because typically if the far point's too far in, the near point's also too far in. And so now I want to correct this. So I want to have a corrective lens. Well, imagine we have a contact lens, so it's right on here. And so what I want to happen is I want an object out here at infinity. So, it could be a tree or something out here at infinity. I want it to look like it is at 1.7 meters. And if that's the case, you ought to be able to see it, or this person ought to be able to see it. So in other words, I have the object distance is infinity. The image distance I want to be minus 1.7 meters. And so in that case, then what happens is that in that case, then what happens is that 1 over F equals 1 over DO plus 1 over DI. That is now 0. So 1 over F equals 1 over DI, and so F would be minus 1.7 meters. Well, in optics, we often talk about the strength of a lens. The strength of a lens is defined to be 1 over F. So that's going to be 1 over minus 1.7 meters. And so that's going to equal to be 0.59 negative inverse meters. So the strength of the lens in this case is a minus 0.59 inverse meters. Well, we have a term for that. There's a unit called a diopter. A diopter is an inverse meter. And so we normally talk about the strength of a lens, 1 over f in diopters. So if you go to the doctor's office, ophthalmologist or optician, and they want to prescribe glasses to you, that's what they would do. Now, that would be the case if we had contact lenses. What if we actually had a lens for glasses? Because that might be different, because this could be 1.7 centimeters in front of your eye. So they have to actually measure that. And so in that case, you have an object over here. You can see out to 1.7 meters. So that means that the image distance, instead of being equal to minus 1.7 meters, it's going to be equal to 1.7 meters. In other words, we want the image distance. The image distance, we want to be 1.7 meters minus 1.7 centimeters. Okay, so that would be 1.7. That would be an image distance of minus 1.683 meters. Well, 1 over f turns out, if you do the mathematics, still to be minus 1. It still turns out to be minus 0.59 diopters. So it makes no difference with glasses or contacts for this person. Well, let's consider another person. So we have another person that's profoundly nearsighted. So their far point, in this case, might be much closer. Their far point might be 23.3 centimeters. Okay. And so in that case, for contacts, when the lens is right on the eye, then we want something infinitely far away. So we want DO to be infinity. We want DI to be minus 23.3 centimeters. So that's minus 0.233 meters. And so 1 over f, 1 over DO plus 1 over DI, that's again going to be 0. So 1 over f is going to be 1 divided by that. So that would give us a minus 4.29 diopters. Okay. But this person's a little bit different. For this person, if they have a far point, and their far point is 23.3 centimeters, if they're wearing glasses that are 1.7 centimeters away, that means the image distance is not going to be 23.3 centimeters. The image distance is going to be a minus 21.8 centimeters. In that case, the strength of the lens is minus 4.59 diopters. So in this case, it actually makes a difference whether you're writing a prescription for glasses or contact lenses. So it's going to be different. The stronger the the stronger the refraction here, the stronger the strength of the lens, the bigger the correction, the more it matters whether you have contacts or lenses. Notice that we have a negative focal length in all these cases. What does a negative focal length mean? Well, a positive focal length is going to be a convex lens. A negative focal length is going to be a concave lens. So this is exactly opposite for mirrors. So for a convex lens, then focal length is bigger than is positive, and focal length is less than 0 or negative for concave lens. Compare that to mirrors. For a mirror, okay, for a mirror, then a concave mirror is going to have a focal length that's positive, okay, and a focal length that's negative is going to be a convex mirror, okay. So this is convex for a convex mirror and a concave mirror and a convex lens are both positive focal length. A concave lens and a convex mirror are both negative focal length. They work very, very similar fashions. So this is an application of this whole thing to the idea that we have corrective lenses. So that's an application of all these lenses and optics stuff we've been talking about.